This lecture is going to start section 6 out of the book. So section 6.1 is dealing with inner products, length, and orthogonality. So first off is the definition. If you have two vectors in Rn, you'll talk about the inner product of those vectors being the number ut, so the transpose of your first matrix, or of your first vector, by v. So u and v are vectors in Rn. What you do is take u, transpose it, so it's a 1 by n matrix, multiply by the n by 1 matrix v. What you get is the inner product uv, or sometimes called the dot product. So in reality, what is this? If u is this 4 by 1 matrix vector and v is this 4 by 1 vector, take u, take the transpose of it, multiply it by v, and just do term by term. You get 2 times 1 plus 1 times -1 plus -3 times 0 plus 2 times 4, which equals 9. Okay, so this dot product or inner product is another way of taking is a way of doing kind of a multiplication of vectors of the same size. So it has some properties that are similar to what you find with normal multiplication if you were just multiplying numbers. You will actually find when you do this that it doesn't matter what order you do them in. Now remember when we did multiplication of matrices, it does matter which order they're in. This inner product of vectors, it doesn't matter which order you do them in. So u dot v is equal to v dot u. You have a distributive law, the same way that you do with multiplication. So two vectors added together, dot product with another vector, you can do the dot products first and then multiply. And again, because you can change the order, remember that this is also equal to w dot u is equal to u dot w. So you can do all kinds of little things with that. Multiplying by a scalar, you can multiply the first vector by the scalar, you can multiply the second vector by the scalar, or you can do the dot product first and then multiply by the scalar. And finally, this is an important product or an important property. U dotted with u is always positive. Okay? Same way as squaring a number, you always get a positive. Well, when you take u dot u for any vector, you always get positive. Every term in it is positive. Or sorry, the result is always positive. And the same way as when you're dealing with numbers, u dot u equals 0 only if you start with the 0 vector. So you can see this dot product has very similar properties to the normal scalar multiplication. Whereas when we talked about products of vectors or of matrices, it had some properties like multiplication, but the big thing that was missing was that a times b is not equal to b times a with general matrices. When you're doing the dot product, you get that property back. So it's closer to multiplication than matrix multiplication is. Another definition, the length of a vector. Now we have a bit of a conceptual idea of the length of a vector. If you take a two-dimensional vector, you can figure out how long that vector is, how long a line is. Well, we can generalize that for larger vectors. And we can write it in terms of this dot product we've just seen. So the length, or it's sometimes called the norm of a vector. So if you hear people talking about the norm of a vector, it's the same as the length of a vector. It's denoted by this symbol here, the double lines. And it is the square root of the inner product of a vector with itself. Or you'll sometimes see it written as the square of the length, or the square of the norm, is the inner product. In the same way, you can take the distance between two vectors. The distance between two vectors, you subtract one vector from the other, and take the norm. That gives you the distance between vectors. And although this property is defined in terms of the inner product, which we've just seen, it is the same as the conceptual idea that you have of distance for a line. So take this for instance. We have two vectors here, 1, 1 and negative 2, 2. We can get the distance of those using that formula. You take u minus v. The distance from u to v is u minus v. So u minus v gives us that, 3, negative 1. Then you take the norm of it. The norm is the square root of the inner product, which is the square root of 10. Now you take this chart, or this graph, you measure that distance. That distance is going to be the square root of 10, using the normal Euclidean distance that you're used to. This is just a slightly different mathematical way of giving you the same concepts. So the distance, defined in terms of this dot product, is the same as the normal distance that you're used to. But I want you to note something about this example. This example in particular has a right angle. So what happens when you have this right angle? Two things that are at a right angle to each other. Well, note one thing in particular. If you have a right angle here, and you take the negative of one of those vectors, that forms a straight line, so you also have a right angle here. So not only so what does that mean in terms of distances? What it means in terms of distances is that distance was the square root of 10, but this distance is also the square root of 10. So when you have two vectors that are at right angles to each other, or when they're perpendicular to each other, you have a special thing that happens. You have the distance that uv is the same as the distance between u and negative v. And think this through, you'll see that this only happens when the vectors are perpendicular. Now, because this only happens when the vectors are perpendicular, we can use this and the definition of an inner product to give us a mathematical idea for when vectors are perpendicular. So we have that the distance uv, we have a formula for that involving the norm. So take the distance uv and square it and rewrite it in terms of the norm. So it's equal to the norm of u minus negative v, which is the same as the square of the norm of u plus v. Okay? Just using the definition that we had a minute ago. Well, what's the norm squared of u plus v? Well, that's the vector u plus v dot product with u plus v. Okay? So that's just using the definition of a norm, or of a distance, and a norm and the definition of length. Well, now one of the properties that we saw of the dot product, you can break it apart. So it's u times u plus v times u plus v. Well, now we've got a couple more here that we can break apart even more. So we're just distributing over the brackets. Now gather these things up. U dot product u is the norm of u squared. V dot product v is the norm of v squared. What are you left with? U dot product v plus v dot product u. And again, because it doesn't matter what order you do them in, that becomes 2 times u dot product v. Okay? So this is just using basic mathematics, algebra, and the properties of dot products to rewrite the distance between u and negative v. Now, take the distance between u and v. Do the same exact thing what do you come out with? Something very similar, except it's minus 2u dot v. But now we've noticed that if two lines are perpendicular, that the distance, those two distances have to be the same. So if they're perpendicular, we have the distance of uv equals the distance of u negative v. Sorry, I just noticed a mistake here. This should be uv, not u negative v. Okay. So these two distances have to be the same. What does that mean? That means that this term on the end, which is subtracted from one and added to the other, that means 2 of u dot v has to equal 0. Okay. So this gives us an idea of perpendicular that works with dot products. In fact, this gives us a whole definition. If we have two vectors, we say that those vectors are orthogonal if their dot product is 0. The geometrical interpretation of this is the dot product equals 0 if and only if two vectors are perpendicular. So we saw earlier that we worked with the vectors negative 2, 2 and 1, 1, and you can see that those are perpendicular. Take the dot product. So that's u and v. So u dot product v is equal to, I kind of wrote those the wrong way, negative 2, 2 times 1, 1, which is negative 2 plus 2, which equals 0. Dot products equal to 0 give you perpendicular or orthogonality. Theorem 2, two vectors u and v are orthogonal if and only if the norm of u plus v is equal to the norm of u plus the norm of v squared. Yeah, squared on all of those. And if you go back to the stuff that we just calculated, you'll see that this only works because u dot v equals 0. So another idea of orthogonality in terms of norms or in terms of dot products. So what this means is that this dot product gives us kind of a sense of things being perpendicular to each other or orthogonal to each other. Let's take a bit of a geometrical concept of this. So if you were in 3 dimensions, again using this kind of sketch of 3 dimensions, what does orthogonality mean? Well, you can have an entire plane. So you have a whole plane here. And what's orthogonal to that? The line that's at a right angle to it, kind of going through the origin, where everything's going through the origin. This gives us a bit of a wider definition of orthogonality. If you have a subspace of Rn, so in R3, what's one of the subspaces of Rn? A plane. So a plane going through the origin is a subspace of R3. What is orthogonal to that? It's a line that's perpendicular to that plane that also goes through the origin. That is a subspace that is orthogonal to it. So if you have a subspace of Rn, take all of the vectors that are orthogonal to it. That is called the orthogonal complement of your subspace, and it's denoted by this symbol here. Okay. This orthogonal complement of a subspace plays an important role in analyzing subspaces. But there's something funny that happens with this in terms of some of the things we've already seen. And this leads us to Theorem 3. We have seen null spaces, row spaces, and column spaces. And we've seen some of the connections between them, but we've seen the connections in terms of sizes. So we've seen that the row space, or the column space, the dimension of the column space, plus the dimension of the null space equals the number of columns. There's even more behind these connections in terms of orthogonality. Take the row space of A, of your matrix. Take the null space of A. Those are orthogonal complements. In other words, every vector in the null space is perpendicular to every vector in the column space. So this is an even stronger relationship between the row space and the null space. Up till now, we only saw that the dimension of the null space plus the dimension of the column space equals the number of columns in your matrix. It's even more than that. Every vector in your null space is perpendicular to every vector in your column space, or in your row space. What about the column space? There's a similar thing. Every vector in the column space is perpendicular to every vector in the null space of the transpose of your matrix. So putting this in terms of the definitions that we've seen, we have the column space of A. The orthogonal complement to the column space of A is the null space of A. And for the row space, the orthogonal complement to the row space of A is equal to the null space of the transpose of A. So this is even stronger relationships between the column space, the row space, and the null spaces. So that's a first look at inner products, length, and orthogonality. We're going to do a little bit more work on these concepts in the next lectures.